Hello everyone, my name is Afrilan from Mujono and my student ID is DSC2409084, and today I'm going to explain about the application of derivative in economics, the Washer method, and the center of mass and moments. To begin, let's clarify what a cost function is. So a cost function is a mathematical formula that allows us to determine the total cost associated with producing a certain number of goods. Now, let's dive into the total cost function, which we denote as C of x, or the one that I written here. It's C of x equals to FC plus V of x. Here, C of x represents the total cost of producing x units of a good, and we have two components to consider, which are F of x with FC, which stands for fixed cost, and these are the costs that remains constant regardless the production level. For instance, it's like rent and salaries, and fixed costs are incurred even when production is zero. And next we have V of x, which represents variable costs. Unlike fixed costs, variable costs fluctuate with the number of units produced. For example, like raw materials and labor cost can vary based on production volume. Transitioning from total cost, let's now discuss the marginal cost function, denoted as MC. Marginal cost is defined as the additional cost incurred in producing one more unit of good. This concept is very vital for businesses as it provides insight into how costs change with an increase in production. Mathematically, we can express marginal cost as MC of x equals to the derivative of Cx. And the derivative of Cx represents the derivative of the total cost function, with this derivative gives us the rate of change of total cost concerning the number of units produced. Now let's talk about the average cost function. The average cost function, denoted as AC of x or C bar x, and C here is a capital C because the cost function is denoted by capital C too. So yeah, it is crucial for determining the average cost incurred to produce each unit of goods. And it's calculated by dividing the total cost or C of x by the number of units produced or x. Next, let's discuss about the marginal average cost or MAC function, and this function shows how the average cost changes as we produce one more unit of good, and this provides insights into the production efficiency. So the formula for MAC itself is MAC of x equals to the derivative of ACX, and here the derivative of ACX represents the derivative of average cost function, and the derivative indicates how the average cost per unit changes when producing an additional unit. Now let's shift our focus to the total revenue function, and this function is essential for understanding how much money a company makes from selling its products or services. And the formula itself is R of x equals to xp, where R of x is the total revenue or total income from sales, and x is the number of units that is sold out or that's sold, and p is the price per unit. Moving on, we have the marginal revenue function, or MR, which stands for marginal revenue, and which indicates the additional revenue gained by selling one more unit of a product. And the formula is MR of x equals to the derivative of Rx, and the total revenue function R of x shows the total income from selling x units, and the derivative of Rx represents the rate of change in total revenue concerning the number of units sold. Next, we will explore the average revenue, or AR function, and this function represents the revenue earned on average from each unit sold and can be expressed as AR of x equals to R of x over x, and the total revenue, or R of x, it's the entire income from the sales, and x is the number or the quantity of units sold. So the next one is a marginal average revenue, or MAR function. It shows how the average revenue changes as more units are sold, and the formula is MAR of x equals to the derivative of AR of x, and average revenue function, or AR of x, shows the revenue per unit for x units, and here the derivative of ARX is the derivative of the average revenue function, indicating how average revenue shifts with each additional unit sold. Now let's discuss the total profit function, which illustrates how much profit a company makes from its operations. The formula is P of x equals to R of x minus C of x, and the P of x here is a big P because small p represents the price, and P of x is a profit, R of x is the total revenue, and C of x is the total cost. Next, we have the marginal profit, or MP function, which indicates the additional profit gained by producing and selling one more unit. And the formula is MP of x equals to the derivative of px, and px is the profit function, shows the profit from selling x units, and the derivative of px shows the rate of change in profit concerning the number of units sold. Next, we also have the average profit, or AP function, which represents the profit earned on average from each unit sold, and the formula is AP of x equals to P of x over x, and the total profit is P of x. It's the entire profit from sales, and x is the quantity units sold, and dividing the total profit by the number of units sold gives the profit per unit, or the average profit. And lastly, let's look at the marginal average profit, or MAP function, which shows how average profit changes as more units are sold. And the formula is MAP of x equals to the derivative of APX, and APX is the average profit function, and this shows the profit per unit for x units. That's an example of the cost function, and let's do it together. So the fixed cost is definitely a constant number. It's not a function, so it's not connecting with x, so we can find a number or a constant that is not interfere with x. So here we can see that 100 is not it doesn't have x, so the fixed cost is 100 because it's the only thing that doesn't interfere with the x. But it depends. If it's C of t, you can find the fixed cost means the number that is not interfere with t, and yeah, like that. So the fixed cost is denoted as FC, big FC, equals to 100. So, and the B1, what is the cost of producing 20 units? So the cost of producing 20 units is just simply substitute 20 to the C of x, which is C of 20 equals to 100 plus 5 of 20, and then plus 0.02 x squared, which is 20 squared. And we can count it from here. 100 plus 100 plus 0.02 times 400, and here we got 200 plus 4 times 2 is 8, so the result is 208. So the cost of producing 20 units is 208. So the next one is find the marginal cost MC of x when x equals to 20. So here, MC of x, the formula is the derivative of C of x, like this. And then y, it is because the derivative of C of x represents how much the total cost will increase when we decide to add one more additional producing. When we decide to produce one more additional unit. So the MC of x equals to, okay, the derivative of C of x is, the derivative of 100 is 0, the derivative of 5x is 5, and then plus the derivative of 0.02 x squared is 0.02 times 2x and the power of 1, but let's just not read it. Let's just not write it. And yeah, and MC of x equals to 5 plus 0.04 x. So the MC of x is 5 plus 0.04 x, right? And the question asks, like, find the marginal cost when the x equals to 20. So we need to substitute 20 here and here, and we just count it. 5 plus 0.04 times 20 equals to 5 plus 0.4 times 2, which is 0.8, which is, it's 5.8. So the marginal cost, or MC of x when x is 20, is 5.8. Okay, so now for the second example, and it's about the average revenue. Average revenue is denoted as AR, so we can write AR of x equals to, the formula of AR of x is AR of x over x, because it's the average revenue. So it's just basically the total revenue over the units sold. So the AR of x is 600x minus 4x squared over x, because it says that quantity of x units each week. So it's 600 minus 4x. And now we need to find the marginal average revenue, or MAR of x, which is the derivative of AR x, and which is the derivative of 600 minus 4x is 0 minus 4, because the derivative of 600 is 0 and the derivative of minus 4x is minus 4, which is minus 4. And now we can calculate the B part with a bit. Okay. The B1 is average revenue and marginal average revenue for x equals to 40. So we just simply substitute the 40 to the x, which is the AR of 40 equals to 600 minus 4 times 40. Yeah, which is 600 minus 160, which is 440. So this one represents the average revenue is $440 for each unit sold. And the marginal average revenue for x equals to 40 is just like this. It's just MAR of 40 equals to minus 4, because we already find the MAR of x and it's minus 4. And there's no x here, so we cannot substitute it anywhere. So the result is just minus 4. And based on the results, explain whether the average revenue is increasing or decreasing at x equals to 40. So because of the marginal average revenue for x equals to 40 is minus, so the average revenue is decreasing at x equals to 40. Okay, so next is the third example, and it's about average profit. So the first one is, what is the average profit function for producing x units? And the second one is, what is the marginal average profit function for the production level x? And the third one is, if the company produces 5 units, what is the marginal average profit at its production level? So check the question here in my laptop. So what is the average profit function producing is, the average profit function is denoted as AP of x, and it's basically just P of x over x. And the P of x is x power of 3 minus 4x squared plus 6x minus 8 over x, because it produces x units. And the result is x squared minus 4x plus 6 minus 8 over x. And this is the average profit function, this one. Okay, and the next question is the marginal average profit function, which is the MAP of x, which the formula is just the derivative of APX. So we just need to do a derivative from this one. So the derivative of x squared is just 2x minus the derivative of 4x is 4, and the derivative of 6 is 0, and the derivative of minus 8 over x. And we just need to count it like minus 8 over x is equals to minus 8x power of 1. So the derivative of this is just minus 8 times minus 1 x minus 1 minus 1. So it's 8x power of minus 2. So it's basically just 8 over x squared. And just write it here, plus 8 over x squared. And so this is the final result of the marginal average profit function. Next one is the marginal average profit when x equals to 5, which is we just need to substitute 5 to this one, to the x. So MAP of 5 equals to 2 times 5 minus 4 plus 8 over 5 squared, which is 10 minus 4 plus 8 over 25. This is 6 plus 8 over 25. If we make the denominator the same, we just easily count the 6 times 25, which is 150. Yeah, 150 plus 8, so 158 plus 25. And this is the final result, 158 over 25 for the marginal average profit when x equals to 5. So the next one is the washer method, and it's used to find the volume of a solid in a revolution when a region revolved around an axis. And unlike this method, which deals with solids having no holes, the washer method's used when the solid has a hole in the middle, creating like a washer shape. And for a solid revolved around the x-axis, the formula is v equals to pi in integral of a to b of the outer radius squared minus the inner radius squared dx. And for revolution around the y-axis, is just v equals to pi from c to d of the outer radius square minus the inner radius square dy. So now let's dive into the specifics. In the Wash method, we define two important things: the outer radius, which is the distance from the axis of rotation to the outer curve, and the inner radius, which is the distance from axis of rotation to the inner curve. And we also need to identify the bounds of the region we are working with, which we will denote as a and b, or c, or and d and else. So now I'm going to tell you about how to find the formula of Washer method. And when the region is revolved around the x-axis, each cross-section perpendicular to x-axis forms a washer or a disc with a hole in the center. And the area of this washer at a given x is the area of outer disc minus the inner disc. So the area of the outer disc equals to pi times big R of x square, and the area of inner disc is equals to small r of x square, and the area of the washer is just simply a of big A of x equals to pi times the big R of x square minus the small r of x square in bracket. Yeah, and then after that, we just need to integrate the function to find the volume and factor out the constant. In this problem, it's pi. Pi is the constant, so we just need to move out the pi outside the integral. Okay, so next one is the example of the washer method. And so here is the graph. I already gave it in the PowerPoint. And this is the x equals to 1 and this is x equals to 4. And this is the curve. So the first thing that we do is we need to identify the function. We need to decide which one is the outer radius or inner radius. So the outer radius is basically the bigger one, which here is the red one because it's above the orange one, so it's bigger. And when the x equals to 1, the red curve is 1, but when x equals to 1, the orange curve is below 1. So technically the red curve is bigger, or the y equals to square root of x is bigger. So here we just write it, the inner radius equals to x over 2. After this we need to set up the integral, like v equals to pi and it's 0 to 4 because the area is bounded by x equals to 0 and x equals to 4. So it's 0 to 4 of the outer radius, which is y equals to square root of x. So we just write it like this, minus the x over 2 square dx. The outer is the square root of x and the inner is just x minus 2, right? After this, we just need to calculate it, and the square of the square root of x is just x. X dx, because I want to split it into 2, and minus the square root of 0 to 4 of x squared over 4 dx. Okay. Like this, and then we can find that we just need to calculate the integral, right? Like the integral of x is x squared of 2 because it's our power function, which is the x bar of r equals to x bar of r plus 1 over r plus 1. It's just like that. We don't need to add c because it's definite integral. Minus this one, we can put up the 1 over 4 because it's constant of x bar of 3 over 3 of 0 to 4, like this. And after that, we just need to calculate it, like we just need to put the 4 and 0. 4 times 4 is 16 over 2 minus 0 minus 1 over 4. We just need to bracket times 4 times 4 times 4, which is 64 over 3 minus 0. This one. And after this, we can calculate it. 16 over 2 is 8 minus 0 is still 8, and minus 1 over 4 times 64 over 3. And this one, and then I'm sorry, this one is this, and this is 8 over 3, right? So the answer is 8 pi over 3 cubic units. So now let's talk about the center of mass and moment. The center of mass of a thin plate with any shape is the point where it balances, and the moment of a particle is calculated as the product of its mass, or m, and its distance from a reference point. For example, as I already drew here, now suppose we place objects having masses m1 and m2 at distance d1 and d2 respectively, as shown below, and then the center of mass of the system is given by m1 times d1 plus m2 times d2 over m1 plus m2. And so the moment is m1 times d1 for the moment 1, and moment 2 is m2 times d2. In general, if n masses like m1, m2, mn are placed on a number line at points x1, x2, xn respectively, then the center of mass of the system is given by x equals to sum I equals to 1 to n mi times xi over sum of I equals to 1 to n mi. So now let's talk about the center of mass and the moment on a line. Let m1, m2, mn be the point masses placed in x1, x2, xn respectively. We need to calculate the total mass of the system, which we denote as m, small m, and this total mass imply the sum of individual masses represented mathematically by small m equals to sum of I equals to 1 to n, denote of the total mass. And the moment of the system with respect to the origin is given by m equals to sum of I equals to 1 to n mixi, and we can derive the center of mass of our system represented by x bar equals to the big M over m, which big M is moment and the small m is the masses. Now let's talk about the on a plane. To analyze the system, we once again begin by calculating the total mass, denoted as m, small m, and let m1, m2, blah 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 until mn be the point masses located in the xy plane at points x1, y1, x2, y2, blah 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 until xn, yn, and let m equals to sum of I equals to 1 to n of mi, denote the total mass of the system. And we need to determine the moments about the x-axis and the y-axis, which is denoted as mx and my, and we use the big M. And these moments are given by the equation of mx equals to sum of I equals to 1 to n of mi, and the big my is also the same. And finally, we can find the coordinates of the center of mass in the two-dimensional system. And the coordinate x bar, y bar of the center of mass are computed as x bar equals to the big My over small m, and y equals to the mx for big M over m small. Next, let's discuss about the centroid of lamina. To begin, let's define what the meaning of lamina. A lamina is essentially a flat plate with a uniform density that occupies a defined region, which we will refer to as R, big R, in the plane. And now let's talk about the center of mass. The center of mass of a lamina is referred to as the centroid of the region R. It is the point where we can consider the entire mass of the lamina to be concentrated for the purpose of analysis. For symmetrical shapes such as rectangles, the centroid is straightforward to identify. It is simply the center of the shape. But however, as we move to more irregular shapes, determining the centroid requires a more nuanced approach. The centroid of the region R is located at the point x, y, where x bar equals to 1 over a integral from a to b of x times f of x dx, and y bar is simply 1 over a from a to b also of 1 over 2 times fx squared dx, where a equals to the integral from a to b of fx dx. Now let's look at the moment of region R about the y-axis. The formula is the moment of y equals to rho times the integral from a to b of f of x dx, and this helps us to find the moment. And here rho represents the density, x is the distance from y-axis, and f of x is the function describing the boundary of region between the interval a comma b, the square bracket. And this integral gives us the total moment of the luminous area about the y-axis. Now we calculate the moment of region R about the x-axis using the formula mx equals to rho times the integral from a to b of 1 over 2 fx squared dx, and it's similar to the previous formula. Rho is the density and fx describes the boundary of the region. The mass of the region R is denoted as small m equals to rho times the integral of f of x dx. So let's now talk about the last example about the region modeled above by the graph of the function f of x and g of x, and we need to find the centroid of the region. So the first we need to find the intersection points, and we can know that the intersection point is where the f of x and g of x has the same point. So we can simply just make an equation of f of x equals to g of x, like this one. F of x is 1 minus x squared, and g of x is x minus 1. So from here we can find the x equals to minus 2 and x equals to 1. And here I already put the graph. Here is the x equals to 1, and here is the x equals to minus 2. And the graph of the function intersects at minus 2 and 1, so we integrate the function from minus 2 to 1. And because the question doesn't contain any rho value, so we can assume that the rho is 1. And first we need to calculate the total mass. The total mass is simply the rho times the integration from a to b of f of x minus g of x dx, and we can just input the numbers. The a and b is minus 2 and 1, and the f of x is 1 minus x squared, and g of x is x minus 1 dx. And then we need to calculate it, and we can simplify the terms like this, and we can integrate one by one, or together is also okay. The integration of 2 is 2x, and the integration of x squared is 1 over 3 x power of 3, and the integration of x is 1 over 2 x squared. And how can we get this? It's just simply the power function. X power of r, the integration of x power of r is x power of r plus 1 over r plus 1. And after that, we can evaluate it from minus 2 to 1, but inputting the 1 into here, and here, minus the whole minus 2 here, and here. And if we calculate, we can find the mass is 9 over 2. And after that, we can compute the moments. The moment of x is this one, the formula. I already showed in the previous slide. And after that, we can input the functions. F of x is this one, g of x is this one. After that, we can find this x power of 4 minus 3x squared plus 2x, and we can integrate this one by one, or together is also okay. And the integration of x power of 4 is x power of 5 over 5, and the minus 3x squared is just minus x power of 3, and 2x is just x squared. And we can integrate it, and we can evaluate it from minus 2 to 1. And then we can find the value is minus 27 over 10. And after that, we can compute the my, the moment of y, which represented by this formula. And we can simply input both functions, and we can calculate it, and then times the inner function times x, and we can get 2x minus x power of 3 minus x squared dx, and we can integrate it to it will be x power of 2 for integration of 2x, and x power of 4 over 4 for the integration of x power of 3, and x power of 3 over 3 for the integration of x power of 2. And we can evaluate from minus 2 to 1. Here I have the calculation, and the final result is minus 9 over 4. Next, we can calculate the x bar. The x bar is denoted as the moment of y over m, and the moment of y is minus 9 over 4, this one, and m is 9 over 2, but minus 1. And we can just simply 2, this is 1, and we can get minus 1 over 2, this one. And after that, we can compute the y bar, which denotes as the moment of y, the moment of x, this should be x, moment of x over m, which the moment of x is minus 27 over 10, and the mass is 9 over 2, but we can just re-proxical because it's times and the function is minus 3 over 5. So the standard of the region is just minus 1 over 2 and minus 3 over 5.